Okay, I think this is actually 4b, not 3b. I think I said that well, it was actually 4a. I think I called it 3a. So I think this is 4a. So yeah, because 3 was Karasuba, Euclid and Karasuba and Strassen. Okay, so the master theorem. I don't have time to show you many examples of master theorem, but you will see lots of examples in the tutorial, and there are lots of examples. So the master theorem, there's actually how to prove it and everything in the book, and you can find fancier versions online. So the master theorem is basically it's a cookbook. It's sort of a plug-and-play way to solve recurrences of the form that frequently turn up when you're doing things like divide and conquer. Okay, lots of things have the right form, not all recurrences. I mean, solving fancy recurrences is an art, and there are recurrences we don't know how to solve. But for the stuff that you frequently comes up, so divide and conquer algorithms frequently give you this, then this usually they have this form. So to get on to more algorithm design stuff, I'm just going to tell you what the master theorem is. So remember, I said when you're doing divide and conquer, there are sort of 3 stages. You take your input, you cut your input, and then you solve the pieces of your input, and then you glue the solution back together. Okay? Now, the master theorem sort of takes me, it's like, okay, there's something that talks about cutting, there's something that talks about recursively solving, and there's something that talks about gluing. Sorry for the clap. So, for example, we saw a couple of recurrences. What is the recurrence relation for merge sort? Which is sort of a very standard recurrence relation. You say, okay, well, we have the formula, the time bound for merge sort, so we're going to ignore this ceiling and floor stuff, because in the master theorem they do. You say, okay, we're going to cut the thing in half, more or less exactly half. So we're going to be looking at, we're going to solve those parts recursively. So we're going to solve 2 problems of size n over 2. So this is going to be a 2 times t n over 2. And then when we solve that, so how fast is cutting? Really easy. How fast, and then when we've solved those, we have to merge them back together again. And that takes linear time. So we get this formula that's t of n equals 2t of n over 2 plus n. Okay? So what about let's not talk about quicksort. I'm going to talk about that in sorting. Let's talk about Karasuba's algorithm, right? Where we do t of n equals, well, we divide it into parts of size n over 2, but now we start out with a multiplication of an n-digit number and an n-digit number, so that's like tn. And then we transfer, now we're multiplying, remember we're doing x1 times y1 is z1, and then we have x0 times y0 is z0, so that's 2 multiplications of number of n over 2 digit numbers. And then we have z1 is x1 plus x0 times y1 plus y0 minus z1 minus minus z2 minus z0. Okay, so that was an addition of an n over 2 digit number, an addition of an n over 2 digit number, and then subtractions of a multiplication of an n over 2 digit number, and then subtractions of two, well, since when you multiply the things get bigger, so these are subtractions of two n digit numbers. Right, so that's actually 3 multiplications of n over 2 digit numbers. Okay, so these two numbers aren't always the same. If they are, good. If they're not, live with it. Okay, but then here, well, what did we have to do? We had to do an addition, so an addition of an n over 2 digit number, which of two n over x1 and x0, so that took time n over 2. An addition of y1 and y0, which takes n over 2. And then a subtraction of an n-digit number and a subtraction of an n-digit number, which, so that's plus 2n. So, okay, we can just write this as 3n. So this doesn't really matter. I mean, if you get it like very close, I mean, as long as you get something that's asymptotically correct. So, okay, good stuff. These two numbers don't have to be the same, like they're not here. Okay, well, what about Strassens? Okay, so that gets a little bit fancy, because you say t of n. This is a multiplication of two n by n matrices, right? And we cut those into, each of those into 4. Right? But each of those is now, each of those quarters is now an n over 2 by n over 2 matrix. So we're still going to have t n over 2. But then if you go through Strassens algorithm, you, instead of multiplying this by this, and this by this, and this by this, and this, and getting 8 multiplications, remember we did all that fancy stuff and we only got 7. And then this thing was something like we had this large, nasty number of additions and subtractions of little matrices. Which, how long did that take? Well, those were additions and subtractions of n over 2 by n over 2 matrices, which takes some number, like it was something like 18 times n squared over 4. So look, it doesn't have to be n here, okay? So you see, like, there are, you know, when you cut, I mean, we could actually do this. I said I was going to send the recurrence. The master theorem, I don't think that solves the recurrence for, not easily. You have to do some tricks. I have to check to see if you can do it in master theorem. For 3 coloring notice, for 3 coloring planar graphs. But in general, you see, like, there is a certain form here. We have t of n equals a t n over b. Oh, so I didn't talk about. I did maybe talk a bit about it. So karatsu is, you can generalize and say, okay, instead of cutting it into 2 pieces, I'm going to cut it into 3 pieces. And then there's a more complicated formula. So I think I said that's called Toon Cook. Cook being Steve Cook, who is Professor Emeritus at the University of Toronto, won the Turing Award. He will come up a lot in this course. He was my logic professor in grad school. He did that, Tim Cook, he did some of the analysis for his PhD thesis at Harvard. Back in like the late 60s or early 70s, I think. Maybe mid 60s. And then this is plus f of n. So I was saying that because if you do 2 and Cook, this b doesn't have to be 2. You can cut things into more than 2 pieces. Right? You can, okay. So in general, you're going to have Tn, so this is the form you're going to look for. Tn equals A times Tn over B plus f of n. And yes, it's a special case, but it's a special case that comes up quite a lot. And actually, not all recurrence relations of this form can be solved with the master theorem. Actually, in the fall section, in the fall semester, I asked something that could not be solved using the master theorem in the textbook, but people went out and I asked them, well, can this be solved with the master theorem? And they went out and found a more sophisticated version of the master theorem online, so I had to accept both the answer yes and no. I don't expect you to do that, just go with what's in the book if you want. So, master method. This is the book from back before Stein joined. This is okay. Tn equals AT n over b plus f of n. So now there are 3 cases which roughly correspond to which of these parts of the algorithm dominate, which is the expensive part, okay? Because you can think, if f of n is huge, then that's going to dominate. I mean, then maybe these pieces, you know, if f of n is huge, and this is going to get small quickly, then you know the cutting or the gluing is going to dominate. Whereas you could say, well, okay, for example, in Strassen's, you know, or in problems like that, you say maybe you cut it into a few pieces, but then you have lots of interactions, like you have little matrices, but they talk to each other, like, you know, even if you cut it into 4 pieces, you're not just solving 4 subproblems. You got this is an A. So it depends on how A relates to B and how A and B relate to f of n. It depends. So what happens? Which case this falls into? So if the cutting and gluing is really expensive, and then the things split up into really small subproblems, then that one step is sort of going to dominate. Whereas if the cutting and gluing are really cheap, for example, okay, so here, merge sort, cutting is really easy. Right? You cut, you do nothing, you recurse. And then when you solve those recursions, the gluing is expensive. Well, not super expensive, but linear time. You have to go through, you get these 2 sorted arrays, and now you have to merge them. Whereas for quicksort, now this is the quicksort, we'll see the analysis, well, we'll see the analysis of at least quick select. For quicksort, the gluing is easy because the cutting is the expensive part. Because remember, you pick a pivot, and then to cut, what do? Well, you divide it into, the cut is you divide it into stuff that's smaller, and you divide it into stuff that's bigger, and then you recursively sort those pieces, and then the gluing, well, you have the stuff that's smaller that's sorted, and the stuff that's bigger that's sorted, and you have the pivot, and you just glue them together. It's like super easy. So for merge sort, cut is expensive. For quicksort, glue is expensive. So really the question is sort of how does the cutting and gluing, how does the expense of this step compare with the expense of the recursive steps? So, so this is, don't worry, like in the fall semester, I will never expect you to memorize this because I didn't. The reason I didn't, remember I said Appel and Haken did the four-color theorem, and it was actually checked by Haken's daughter, who became my third-year algorithm professor. So the master theorem is actually by Bentley, Haken, and Sachs. That Haken was not the four-color theorem of Haken. That Haken was his daughter, who was my professor, algorithms professor. Haken was her maiden name, and so I didn't know that until at some point I found out that she had been Dorothea Haken before she got married. And then, so I knew her as Professor Lostin. Oh, look at the nice sunset. Should I pause? Should I keep going? Okay, I'll just finish this. Maybe it'll still be there. So again, okay, I'll copy this. You have, suppose you have a recurrence, so let A greater than or equal to 1 and B greater than or equal to 1. Be constants. Let f of n be a function. Oops. And let T of n be a recurrence relation. Recurrence of the form T of n equals A T of n over B plus f of n B. And we ignore n over b, could be floor of n over b or ceiling of n over b, we don't care. Okay. Then Tn can be bounded asymptotically by as follows. So, I guess we have three cases. If f of n is O of n log b a, I hope you can see that. It'll be in the script notes anyway. Minus epsilon for some constant epsilon. Then T of n equals, see, this is what I mean about they draw equals. Even in the book is theta n log b a. Okay, so what is this saying? This is saying that f of n is small. The cutting and the gluing are cheap. relative to sort of the recursion, okay? So the recursion is going to dominate, okay? In particular, the last step of the recursion is going to, I mean, if you think of the recursion as a tree, what's going to hurt is going to be the fact is the leaves of the tree are each cheap, but there are going to be a lot of them, okay? So, because how far down do you go? I mean, if you think of the tree, you're sort of the branching factor is A, and the depth is going to be like log bn. And so how many leaves are you going to get? I shouldn't do this stuff on the fly, but you're going to get something like, you're going to get a to the log base b of n, which is going to be, which is a to the log n over log b. We can write this as 2 to the log a times log n over log b, which is 2 to the log n, because we can swap these because we're multiplying, 2 to the log n, blah blah blah, log a over log b. And this is just n to the log base b a. Okay, so how many leaves are you going to get? Blah. Okay, so this is, in this case, if f of n is small, you're going to get killed by the number of leaves. Okay, when you divide it down, the number of little tiny subproblems at the end, that's what's going to hurt. Okay? It's the end of the day, and yeah. Okay. Then it's if f of n equals theta, n log b a, then t of n equals theta n log base b a log n. So this is saying, okay, now the cutting and the cost of the cutting and the gluing is sort of balanced against the cost of the recursion. To remember this, think of merge sort. Right? For merge sort, a was 2, b was 2, and f of n was n. So n to the log base 2 of 2 is n to the 1 is n. So in that case, you get n to the 1 times log n. So that's how you remember. Now, these things, you've got this, so far you've got log base b of a. Okay, so if it's not 2 and 2 and n, but it's something else, it's like a is 3 and b is 2. But then instead of having plus n, you have plus n to the log base 2 of 3, then you get log base 2 of 3 times log n. Okay? And then the last case is the case I was saying where the cutting and the gluing, that part kills you. So, equals, this should be, yes it is. So this, remember, if f of n is at most, now this part, when you stick the epsilon in, you're saying it's at most this minus epsilon from some positive, so this is strictly smaller, but this is actually a stronger statement than saying it's little o of n to the log base b of a, because n to the log base b of a would include things like n to the log base b of a over log n, which is asymptotically much bigger than this. Okay. So if f of n is, so this is at most, this is, yeah, like roughly equal to, and this is n to the log base b of a, I believe, plus epsilon for some positive constant epsilon, for some epsilon greater than 0. I'll just make sure that's true. Oh yeah. And then you have this nasty condition. And if a times f of n, f of n over b, less than or equal to c times s of n, less than or equal to c times f of n, for some constant c, for some constant c less than 1, and all sufficiently large n, then Tn equals theta f of n. So this is the case, period. So this is the case when the cutting and the gluing dominate. It's like, yeah, okay, you're going to maybe you're going to shrink the algorithm, you're going to shrink the instance of the problem so much that that dealing with the subproblems are going to be really cheap. You know, there aren't that many of them, and they're easy, but it's the cutting and the gluing that are going to kill you. So, so for example, if I came up with some silly way to do a merge that took quadratic time. So I say, oh, I have this cool algorithm, I have this sorting algorithm or something, and I think it's going to be like merge sort, where, I mean, obviously if it takes quadratic time to do the cutting and joining, then it's not going to take some quadratic time. But if I said, if somebody came and said, oh, I think it will do this, it's going to be, so I'm going to cut it in half, and then I'm going to solve each of the two halves, and then but the cutting and then I'm going to glue them together, and I'm just going to take quadratic time to do the gluing. And then you say, yeah, well, that's not going to work because, yeah, when you cut it in half, it's going to get smaller and less easy, but this gluing step is going to dominate, and that's because you're going to say, okay, f of n squared is in n to the 1 plus epsilon for some positive constant epsilon, and then you have 2 times f of n over 2. So this, actually I just have to check this. So you have 2 times n over 2 squared. That is going to be 2 times, it's going to be n squared over 2. And so this is true for c equal to 1/2. Because this is f of n is n squared, so this is going to work. And so you're going to say, yeah, okay, actually your algorithm is going to take quadratic time. So you'll see more cases. There are lots of cases of this online. I just wanted to get, to go through sort of, don't worry, on tests, assignment, like whatever, where you have to do it, I will cut, not physically cut, I will take a picture of this page, I will cut the theorem statement out and I'll give it to you. So you just have to learn how to use it. So I will try to record the 5th lecture over the weekend, and then we'll be all caught up. Good luck with the homework. Good luck with the tutorial section. Please say hi to the TAs. Have a good long weekend. Cheers.